All right, let's make, that seems to be working. For some reason, when I plugged it in, the default was to have the mic muted. So hopefully that wasn't true last recording.
No, I was able to watch it just fine.
All right. I'll extend the same invite to everybody. There's a free breakfast upstairs. It starts 5 minutes ago. For celebrating MLK Day. Just go up there, get some free breakfast, listen to I Have a Dream speech. Stick around to discuss. I think they're doing a discussion afterwards, but people oftentimes just, grab some food and leave after that. If you want to go do that, open the door to you. I record all the lectures and everything. If everybody goes up there, we'll just start lecture a little bit late as well. But I mentioned that to a few of you already, and nobody's gotten up to walk out the door that way yet. So then so in which case we'll just go ahead and start lecture. Let me get power. Oh, that's why. Hang on. Again, I tried to start all this up before I, so it really confused my computer. And yeah, hang on. What is going on here? What happened to my? Hang on. Gotta get all the displays on again, apparently. I thought I had it turned on, but it appears not. All right. Yeah, the TV is working now at least.
Exactly.
Cool. All right. So lots of good quiz questions this week. One that applied more to ozonolysis. We'll talk about later. What else what other metals show up in heterogeneous catalysis? It's a little bit of an empirical process where they try metals and then they see what works and what the yields are, and then they try other metals. They just kind of use like, okay, well, for whatever reason, and usually if you go deep enough into orbital theory and material science, you can usually explain why some metals work better than others, but it depends a lot on the exact reaction and what you're trying to accomplish. The ones that we'll see in this class of platinum and palladium, and we will see a version of nickel. It's really interesting. It's called a poison catalyst, where it facilitates the reaction happening once but not twice. That specifically works for hydrogenation of alkynes, where you want to have, if you have 2 pi bonds, but you only want to hydrogenate one of those 2 pi bonds, you can use a poison catalyst and it'll catalyze breaking one of those, so you're left with an alkene instead of an alkyne or an alkane. So there's some weird stuff like that. Tungsten shows up a couple times. But basically on a case-by-case basis, it's going to depend on the functional group and what the actual reaction is. But those are the ones I think that are most common. Mercury, not usually in heterogeneous catalysis. We see mercury a lot in homogeneous catalysis or as a reactant like oxymercuration. Also worth noting, who remembers the difference between a catalyst and a reactant?
Catalyst brings the activation energy down.
It does. What makes it different than a reactant though? Because reactant could bring the activation energy down too.
It doesn't get used up if it stays. Yeah.
It doesn't get used up. So basically you end with as much catalyst as you started with. And that's really the big difference between. So mercury in the oxymercuration is a reactant, but the platinum in hydrogenation is a catalyst because it doesn't get used up. And we'll do a lot with acid catalysis in this class too, where you need the acid, you need the H plus to start the process, to hydrogenate some, or to protonate something to start a process. But then over the course of the reaction, you regenerate that H plus. So it kind of gets temporarily used up. But because the net reaction doesn't involve that, so in acid catalyzed hydration, we had to start with an H plus so that these can come over here and attack to make our intermediate. And then we can have, if we have water, then come in and attach to the other side, then we still have an oxygen with too many bonds at the end, right? And so we have to do that last protonation step to kick off one of these H pluses. That's the part that's regenerating the H plus you started with. It's not the same hydrogen. Which makes it seem on the surface like H plus might be a reactant, but because the net product or the net reaction doesn't have that H plus as part of the product and reactants, it is technically catalysis, even though it goes through this process where it gets temporarily used up and regenerated. Epoxidation, when we talked about epoxides, I mentioned epoxies, epoxy resins. Epoxy resins work, it is just actually, it's kind of just a clever rearrangement of regular ring opening reaction that we saw already. For a ring opening reaction, we saw it with taking an epoxide group and then just having water act as a nucleophile to attach, so we get that dihydroxylation. If you use something that's not a water molecule, like say another alcohol, you actually wind up whatever's on the other side of this oxygen gets attached here. So this is actually the first step. So this would be the two different molecules that are in the two tubes when you do an epoxy resin. This is the exact terminology depends on what brand you're using, what the exact reaction is, but basically this is the molecule that's going to make most of the polymer up, and this is what you need to start the reaction. So this is going to be in one tube, this is in the other tube, and what happens is when you mix these two together, you wind up attaching, so this molecule here turns into that piece right there. It just attaches to this larger molecule, and it'll do it on both sides. So we have two of these, so we watch our stoichiometry here. And so we wind up with this happening, but this, if we have it in the right conditions, will actually reform an epoxide. It'll kick off the chlorine and turn it back into an epoxide. So basically this is kind of like a primer. And now this is going to be our actual reactive molecule, because then this then turns around, if we have this molecule we just made, and we have some of these other BPA, these bisphenol molecules that haven't reacted yet. Now all of a sudden we have more alcohols that can attack here, right? And so this is an autocatalytic reaction. This reaction will keep itself going, because in the process of this molecule reacting here, you'll actually take this oxygen on the other side and it can wind up turning back into one of those. And so you wind up with this process where we wind up with a continuously growing molecule, where every time one of these reacts with another one, this molecule gets 1 unit longer, but then you regenerate the reactive group on the end.
And then because it has that OH in the top middle, it forms like a complex bridge structures, because that can also react with
Right. This could then react with another one of these as well. So you don't even just get one long polymer, you get it cross-linked, they call it. Instead of getting like long strands of spaghetti, imagine making all these long strands of spaghetti where you're attaching spaghetti to the other noodles in the middle as well. You don't get just a bunch of long things kind of nestled together. You actually get one cohesive molecule at the end. Once it's all fully reacted. And that's why it takes a long time for this process to finish, is those last cross-linking reactions can take a while. But that's why an epoxy resin is so durable, is because it literally is the entire thing. It's one covalently bound molecule. And what's why it, it won't dent anymore or anything like that. While it's still hot, while it's still curing, you can still wind up with it it goes through that intermediate where it's sort of like a gel. You can't really work it or change the shape, but it can be dented. That's basically when it's not done yet. It's mostly set. It's turned into a solid. A lot of your solvent is evaporated out, but it's not all the way done reacting yet. And a lot of polymers are going to form the same shape. Polymer in general just means you have one unit that's repeating for an indefinite number, and it can be cross-linked like this one, like we just talked about. But basically, you wind up with this, and you see this bracketed piece here that just has n number of subunits. N can be anything. You can control what n is a little bit, depending on what the actual mechanism is. Not all polymerization reactions go through the same mechanism. So depending on what the mechanism is and what your actual stoichiometry is, your n is going to change a little bit, which can change some properties, like why some plastics are more flexible than others. Has to do with how long the actual chains are and how much cross-linking there is, and actually what these pieces are. Like polyethylene is a really, really simple one. Polyethylene is just a whole bunch of ethene molecules that you then let them react with each other. So if you have N ethylene molecules, if you let them react together in the right way, you get CH2, CH2. It's N long with a methyl group on each end. So that's all polyethylene is basically an indefinitely long alkane.
How do they manage to get like dyneema, which is like literally a polymer of like millions of, that's what's like.
You just let it keep reacting.
Okay.
You let the reaction keep going.
Okay.
Depending on what your actual initiator molecule is that's starting this process and what your actual stoichiometry is, you can let this reaction go or you can stop it. If you want it to be a bunch of shorter polymers, if we wanted to make a plastic that was going to be, say, soluble in acetone for whatever reason, we want to make it so that we can break it back down and recast it. We don't want N to be that large because we want it to still stay soluble, not all be one cohesive molecule or all tangled up. So you would control your condition so that N was 100 or 1,000. If you want to make something that's not going to dissolve in other solvents, then you want something more permanent, then you make N larger or you change this. Like instead of having CH2 as your unit, they call that a monomer unit. A bunch of monomers put together becomes a polymer. If you put a chlorine on one of those, now it's PVC. So the difference between polyethylene and PVC is you put a chlorine. PVC stands for polyvinyl chloride. The monomer unit before it reacts, CH2 double bond CHCl. The name for that, the common name for that molecule is vinyl chloride. So polyvinyl chloride is PVC, which is also the same molecule that you make vinyl flooring out of. For whatever reason, you don't call it PVC when it's being used as flooring, but you call it PVC when you're using it as a pipe. It's the same molecule though, slightly different properties, thicknesses, durabilities, that are all based on how they process it. So polymerization is actually an entire grad school, like field of study. You can get a PhD in polymer science. It's a subset of both chemistry and material science. And you can even do things like part of my grad school research was looking at polymers that we could use as photovoltaic material. So plastic, carbon-based photovoltaic solar cells. And we were looking at controlling that process by actually making it so that the process didn't go indefinitely, that we fed it one set of reactants at a time, so we could build it up one monomer at a time. And get a really closely controlled length of these polymers, which is kind of how they make OLED phosphorus, the bits in an OLED that actually glow the different colors. Are basically made by making these conjugated pi systems, these aromatic molecules where you've got conjugation between them that are a certain length. Because changing how big your extended pi structure is changes what that gap is between the HOMO and the LUMO, which changes what color it glows when you apply current to it. That's awesome. It is. It turns out LEDs and photovoltaics are the exact same principle used backwards. So if you apply a voltage and current, you get things to glow certain colors. If you apply light, you get it to produce a current at a certain voltage.
That kind of like similar to the research that's being done with like the nanoparticles
Mhm.
used in photovoltaics to get
Yeah.
specific wavelengths.
Yeah, so that gap in between the HOMO and LUMO, when we're talking about individual molecules, we call that the HOMO-LUMO gap. But when you apply that to an entire material, they call it the band gap. Basically the law of large numbers and the statistics come into it, and you wind up mixing these orbitals together. But that's exactly what it is. Band gap is what controls what wavelength of light a semiconductor will absorb to produce current, or it'll affect what wavelength of light it produces when you supply the current. And it turns out changing the size of those molecules changes that band gap, which changes the wavelength of light. All right, couple other quiz questions here. Can dihydroxylation be conducted with nucleophiles other than water or oxygen? So we just saw an example of using an alcohol. So it's not dihydroxylation in that case. You wind up making an ether on one carbon and an alcohol on the other. But yeah, there are other analogs to epoxides that where it still makes a three-sided ring like that, but where it's not oxygen. So that anytime you've got a ring structure in organic chemistry, and one of the rings is not, or one of the pieces of the rings is not a carbon, we call that a heterocycle. But you can make a heterocycle with a nitrogen instead of an oxygen. You actually see it really commonly with sulfur, because sulfur is a little bit larger, it's a little bit more stable. They call them episulfides, like epoxide, that's sulfide. This is called an aziridine, if I'm remembering correctly. But yeah, anytime you've got this three-sided ring structure, you can change what you're left with when you do a ring opening reaction. And if you change your nucleophile, you change what you're attaching to the other carbon. So if you could do a diaminification, I guess.
I tried to come up with
So nitro, I'll be careful. You're close. Anytime you see, and I actually missed this. Anytime you see nitro, that usually means a nitrogen with oxygen. It's like an NO2 group getting added to something is a nitro group, but an NH2 adding to something is an amine group. So subtle difference. But yeah, it would be, I don't actually know what the name of that reaction will be, because it's going to be a pretty, niche reaction. Not everybody's going to need that one. But yeah.
Junior tried saying diamine.
Yeah, and when you do wind up with a lot of these things where if you just see them written, like you're not going to pronounce it right, even with just some of the element names. Mendelevium. If you know who Mendeleev was, then Mendelevium is really easy to pronounce. But if you don't know that, then who knows how you're going to pronounce it, right? But yeah, and we will see a continuous, like a ring up a three-sided ring, going through a ring opening reaction is going to be a pretty common theme as we get further and further in. It's not, we don't make these that often because they're not super stable, but when we make one of these, the next step is almost always nucleophile attacks and you do a ring opening because they're not going to stay like this very well. And then last but not least, if we have benzene rings, can we go through these same hydration reactions, alkene reactions with all of the pi bonds? Yes and no. They're not gonna, yeah. It's not that the reactions are more unpredictable, it's basically that because it's an aromatic, because you have those alternating pi bonds, there's actually something special that happens with the orbitals. If you have an odd number of electron pairs arranged in a ring, you actually wind up with a sort of bonus to your stability. It's way more, makes it way more stable than just 3 pi bonds should be. So basically, benzenes won't go through any of these reactions we're talking about because they're too stable as they are. Under the right conditions, you can force benzenes to react with some of these, in particular hydrogenation. You can hydrogenate benzene and turn it into cyclohexane by just really catalyzing it and having it react at like 100 atmospheres of pressure. You can get it to react, but it's really, really stable the way it is. So for the most part, all of these reactions are excluding aromatics. And we'll talk about aromaticity in more detail and why that is when we get there, but it's not just that they're unpredictable, it's basically that they're non-reactive.
Well, my thought would be like, is it just because the electrons are delocalized, it's a completely different like orbital than just a single like pi bond would be?
Yes, basically you wind up, remember the way we can mix these different orbitals together, and by mixing them together in a way that where they're all in phase with each other, you actually make some really, really low energy orbitals. And so your homo-lumo gap in something like a benzene ring is much larger than just in an alkene. And a homo-lumo gap is also a pretty good way of looking at how reactive something is. Because almost always for something to react, you have to break up the homo and put more electrons in and move electrons around. So if you have a really, really big gap in energy between your highest occupied orbitals and your lowest unoccupied orbitals, those tend to be really stable molecules. And benzene is a classic example of that. All right, and I did not look at everybody's answers yet. How did we feel about these questions though? Worth going back through and double checking them?
Yeah.
Okay, good practice.
This was a great way to like review too, like go back and look at every reaction, figure out which one.
Seeing them all next to each other could be really helpful, especially for studying. There's a reason why they do these reaction summaries sort of on one page. So that you have sort of a cheat sheet to look back to. If we're trying to do the Markovnikov hydrobromination, all we need is HBr, right? If we're doing anti-Markovnikov, same thing, but we added what? What is it that made it?
Hydrogen peroxide.
Yeah, some peroxide.
Peroxide of some
Peroxide
sort.
in general, yeah. So we still want HBr as our reactant.
Yeah.
And this is actually, the peroxides in this case are actually sort of a gray area of catalyst versus reactant. They do get used up, but they're not part of the reaction. So they're what we consider an initiator molecule. They get used up, but they're not part of the net reaction, which seems contradictory. But basically, you'd also be making plus H2O on this side as well. You wind up with the H2O2 breaking down, but that's not part of our organic molecule, so we just usually leave it off.
I just put down as that like ROOR. That's
Full credit as well.
Yeah.
Means the same thing. They're both a peroxide, especially since we just need it as the initiator. Doesn't matter which of those you're using. Anti-Markovnikov hydroxylation, or sorry, hydration. That's going to be our hydroboration, right?
Yep.
EH3 in THF. And then second step is hydrogen peroxide in NaOH. Dihydroxylation, did the stereochemistry matter in this case? Didn't matter if we did a SYN versus an anti-dihydroxylation, so either dihydroxylation works, either the OSO4 or,
That's what I chose, because I kind of figured that it didn't matter.
Yeah.
With that one.
making the halohydrin, we start by adding the bromine and then we add the water, right? So. And really, it's really kind of one step. It's if you do add bromine in the presence of water, you're gonna get this reaction. You're gonna get it mixed with some of the dibromination product as well. All right, then we've got. If we're looking here, Markovnikov, so either acid catalyzed or oxymercuration.
I chose oxymercuration.
Generally has a higher yield, so it's usually a better option. So step one. HCO OAC2. Step two. We use NaBH4, right? Basically just need a reducing agent to do that second step. And I guess I didn't fill in there. We'll spend, this one is where we actually care about which we need, right? So to get to, once we make bromination, we can then go through an elimination, right?
I put down TBOK, because I was sort of assuming that it was gonna go through E2.
We want a sterically hindered base is actually ideal, because we want a strong base that's not a strong nucleophile. So TBOK is perfect, or either any of those other ones.
Would you, would you get double bond on the like little metal sticking up top? It's less substituted.
That's a good point. So maybe we don't want TBOK because that's just gonna undo it the same way. So we need a strong base. We're just have to deal with the fact we're not gonna have a great yield. So we're gonna get some substitution product.
Yeah, I didn't think about that.
Yeah,
NaBT.
that would work. Yeah. Yeah. And was that I'm not feeling great. I'm gonna run to the restroom real quick.
Okay.
Go ahead and talk amongst yourselves for a second, and we might be ending class a little earlier than I thought.
Okay.
I'm kind of turned up on my head on this Markovnikov, anti-Markovnikov.
Okay, first two things that we went over. Markovnikov. The rest of the shit, anti-Markov.
So Markovnikov is when the more substituted carbon is attacked by.
And it receives the thing that's not high.
Yeah, that's what
Yeah.
that's what I'm.
So just acid catalyzed and oxymercuration, that's it.
Oh, you know what?
And then all the rest of the reactions, you have to worry about if it's anti or acidic.
It was, I shifted the reactants from like.
Or like hydrobromination is Markov. So it's like the VR attaches to the more substitute. But then when you add the peroxide.
That's where I got it fucked up. I said H2O2 on Markovnikov, and that's not.
I for some reason wrote PR2 and H2O2 to the top, and I don't know.
Yes. Well, maybe.
Yeah, I was like.
I put it down, I don't know, I hope we get some full credit off. Bro, I don't know, a couple of weeks here.
But for the syn dihydroxylation, what would we?
That's the awesome.
That's what I was thinking about, yeah, that one keeps them on both planes.
And the other ones.
Compared to the other ones, the
RCO3H, which
Yeah.
is, I think I wrote
and
down.
then you just add,
Peroxy.
and then you just add acid, yeah, it comes from acid.
And the enhancing. Right?
Mm-hmm.
Oh, I fucked up one thing on this.
There would be, yeah, other than, I like to use like a P for the
Yeah.
That makes sense. To the favor the thing too, yeah, so it's like that.
That's it, you give you something good,
So fucking long.
no, this is gonna be a great study.
And I opened the quiz and I was like, oh.
It's 2 questions. I was like, how many PDFs can I make this time?
All right, so we will end this a little bit early. I'm glad I had
Feeling
light
okay?
breakfast. I'm not feeling great, so we won't have a lab. We talked about that earlier about whether it was gonna be a paper lab or not.
Okay, so it's paper lab.
We'll do a paper lab today. Which is okay, because I think that's what we did last year. I'm looking at the timing of everything. You got a snow day on the third Tuesday last year,
Will we get to that
Um,
acid catalyzed hydration
next week.
next week?
Yeah, so we'll just push everything back a week. I have printouts for you and I'm feeling temporarily better, but I don't want to chance it, so I'm gonna talk about oxidative. Cleavage real quick. It'll just be a quick couple slides and then take your paper assignment. We're good.
It was kind of different.
All right. Pass those around.
We're gonna discuss the final products.
Cool. Thank you. And the big difference was we used the peroxy acid to make an epoxide here and then just did water as ring opening. This one we use the OSO4, the ozone tetroxide. That's just a hydrogenation with platinum, yeah. All right, so oxidative cleavage, more commonly called ozonolysis. Oxidative cleavage is the formal name that describes what it's doing. You're gonna oxidize it and you're gonna break it into pieces of cleavage, like you're cleaving something with a meat cleaver. And it just works. It's really easy to recognize. This is why it's called ozonolysis. Ozone and lysis. Anybody know the Latin for lysis? What does that mean? Break apart, split. So ozonolysis just uses ozone to split stuff into pieces. And what the net result is you're just gonna take this alkene group. There's a version of this for alkynes too that we'll get into on Thursday. Take this alkyne group and you break it apart, break both carbon bonds, and you put a carbonyl on each side. So the net result is pretty straightforward. And literally the way I draw this, just draw a slash through that and then take this piece and this piece. And where there was the pi bond, you just add a carbon oxygen double bond. All right, the mechanism looks a little bit scary. Because it does go through this sort of spontaneous rearrangement in the middle, and that's what actually causes the cleavage to happen. Is ozone comes in here, and the Lewis dot structure for ozone looks like this, where you actually get a polar molecule out of all oxygens, kind of, because the resonance structures put extra negative charges at each end and an extra positive charge in the middle. So it's not truly a polar molecule because you don't have polar bonds, but you wind up with these sort of partial charges at the end.
So it acts like one, but it is.
Exactly.
Yeah.
And so you make this sort of 5-sided ring structure that's almost like an epoxide. So you can picture doing an epoxide where we're attaching 3 atoms to each carbon instead of 1. So you get this initial state that looks pretty, the arrows look a little convoluted, but it's sort of going in a ring structure, just like we saw with the epoxidation, right? The electron movement is in the same general direction. They're drawn as clockwise here, but you could draw it counterclockwise as well. But you get electrons move to one end of the ozone, pi bond moves over to the middle, electrons from the other end move towards the other end of the pi bonds. And then the trick is that it sort of like detaches and reattaches. these second two steps are the tricky steps. And so this initial product is called molozonide. And then it will spontaneously rearrange itself and break the carbon-carbon sigma bond, which we haven't seen yet. That's the new piece. It breaks the carbon-carbon sigma bond to make a carbonyl. And so, and then you wind up breaking one of the oxygen-oxygen single bonds as well. So you wind up making a carbonyl on one side and sort of a carbonyl with a peroxide bond attached on the other side. So you make this thing that's really not stable, and it really is kind of, it doesn't fully detach. Because it just basically rearranges itself to look like this. This is the more stable intermediate, stable enough we can actually isolate it and characterize it, called an ozonide. So again, kind of looks like an epoxide, except we have this piece attached in between the two carbons now, instead of just the two carbons attached to each other. If you take the ozonide and you give it just when they say a mild reducing agent, it's a reducing agent. We want to take this and we're going to reduce it slightly. But we're not going to use something as strong as a hydride to do it. So the most commonly you see DMS, which is dimethyl sulfide, or you see zinc metal with water. And what that's going to do is, and again, that goes through slightly different mechanisms, and those steps aren't as well understood. So I'm not going to ask you the mechanism for the second piece. But the net result is that one of these oxygens attaches to each of our R groups. And we make two carbonyls. And then we also wind up with either the DMS or the zinc gets oxidized by the last oxygen. You basically, the second step is putting something in that also wants one of these oxygens. This isn't super stable because you still have an oxygen-oxygen single bond. And so if you have something else in there that also wants an oxygen, it'll basically steal one of these two oxygens and dump it onto the zinc or onto the dimethyl sulfide. So your other product would actually be plus a zinc oxide or DMS, dimethyl sulfide, turns into dimethyl sulfoxide, so DMSO, which is another one of our non-protic polar solvents, back from last quarter. All right, so but for the most part, this mechanism is one of the reasons why ozone gets used for purifying water, because any bacteria or viruses in water, almost all of them have alkene groups, especially bacteria. Those phospholipid bilayers get broken up really, really easily by ozone. So it's a really effective way to treat contaminated water. It doesn't remove the chemical aspect, but it kills anything living. And so you'll see that sometimes basically you just have an ozone tank and you just pump ozone into a holding tank. And that's going to kill anything living. And then when that happens, usually you wind up with either like sort of a scum, a bunch of non-polar stuff floating on top, or a bunch of protein stuff floating on bottom that's not soluble in water, but it's not living anymore. And then you can just sort of scoop it out.
So is that how the water is filtered here, or is it a different way?
So I think that Stupid uses UV. That's the other common way to do it, is you just bombard it with high energy light till everything's dead. And then same effect, once the cells are all dead or the viruses are all denatured, then they don't stay soluble and you get the different layers. So you get decent water in the middle, you get gross stuff on top, gross stuff on bottom that you can just physically remove by scooping it off. Anybody ever had a saltwater tank for fish? They have this thing called a protein skimmer that you have to have if you have a saltwater, especially if you have a reef tank, that's basically just buildup of excess proteins and stuff like that. That kind of makes this sort of gross, foamy scum on top. And you literally just sweep it off the top. All right, so net result of that is just, there's one example here we'll do just before we end. believe that I put an ozonolysis on here. Maybe I did, no, not here. All right, so. I'll redraw it since it's off the bottom of the page there. So if we put this molecule through ozonolysis, this is also another good example of benzene won't react through ozonolysis. But any other pi bonds will. So if we have enough ozone, then any carbon-carbon pi bond aside from aromatics gets chopped up. So we're actually going to break that bond and that bond. It does rely on stoichiometry. If we only had one equivalent of ozone,
Then it would only break off.
it would break one of them and we'd probably get a 50-50 mixture. Did it break that one or that one? And just probability based for the most part. As it is though, and especially when it's a more complicated one like this one's not too hard to see how that's gonna work, right? We're gonna wind up with an O here, and then acetone is our other product, right? This one's a little bit trickier to see because it's a ring that we're breaking apart. But with these, when you do the ozonolysis, the way that I can draw it the best is usually try to leave everything in the same spot. Don't try to unfold it. When you first draw it, just do this and draw sort of a oxygen there and an oxygen there, and then you can try and pull it apart.
So you get the right number.
So you get the right number of carbons. Otherwise, there's a tendency to either add an extra carbon or you lose a carbon.
With a function for one of our.
Exactly. So now we know, we can look at it and say, okay, well, it's gonna be 6 carbons long, then aldehyde at each end, and a ketone in the middle. So then if you could answer it just by leaving it like this. If you wanted to draw it the more standard skeletal structure way, then we could do 1, 2, 3, 4, 5, 6. Aldehyde there, and then on carbon 3 is another carbon here. We won't deal with naming that at this point. And plus acetone, obviously that other piece, that small piece we broke off initially. And you can see how it'd be pretty easy, like there's a lot of molecules like this in bacteria, in proteins and stuff like that. So it doesn't matter that we still have all the same number of carbons there. They're not going to be keeping the cell alive, protecting the cell. They're just going to basically fall apart into this gross mixture of organic stuff that's no longer living or dangerous. All right. We're gonna end there. This will be your assignment for this afternoon. I'm gonna go home and look down.
As you should, please feel better. Yeah, feel better.
Thank you. I've never had that happen. I've gotten like delirious from a fever setting in while I'm teaching. I've never had a digestive issue come in while I'm in the middle of teaching, so
Yeah.
that's a first.
Fish for breakfast.
Well, you put me down.